Hi there, thanks for joining us. This is Space Nuts, where we talk astronomy and space science and recipes sometimes. Well, we're going to talk cooking today, believe it or not. That'll be coming up. I know that sounds strange, but we do cook with light, and somebody's asking if we're doing it the best possible way with microwaves. Is there a better way? We will investigate that. I might as well go backwards. We're also going to be hearing from Rusty in Donnybrook, who thinks we ought to redefine a situation that changed, I think it was 2006, and define the changes in our outer solar system by giving two dwarf planets the characterization of a binary planet. We will argue that. We'll also look at some galaxy mapping, and the wonderful moon Enceladus is back in the news. We'll talk about that too. All coming up on Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining us to talk all things astronomy and space science, as usual, is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. It seems like years since we've met.
Oh, it certainly feels like yesterday to me.
Oh, right. Okay. Maybe it was.
It could have been.
Yeah, it could have been yesterday.
It's the beauty of podcasting. You can do 20 of them in a day and spread them out over half a year and no one would be the wiser.
There wouldn't be any the wiser, but you would be completely bonkers by the time you'd done 20 of these.
I think so, yeah, indeed. How are things, by the way?
Oh, a bit damp here in Sydney, like they are up in Dubbo for you. Sadly, of course, this week is when our roof maintenance was being done, which consisted of removing all the ridge tiles, removing some tiles that were broken, and a few other things as well. And it's not what you want when it's raining.
You absolutely know when you do that job it's going to rain.
Yeah.
It's the same thing that happens when you wash the car.
I never do that.
Rain the day after. Yeah. Anyway, well, we, you just have to grin and bear it, I suppose.
They've done a very fine job of making sure the house is watertight, and I hope it still is, because I don't think they're going to come back tomorrow. And they've still got work to do, and there's still holes in the roof, but I think they're all blocked up.
Fair enough. All right.
He'll be right, as they say in Australia.
That's right. We do, don't we?
He'll be right.
Okay.
Yeah.
Now, let's talk about Enceladus. This is an ice moon, and we've learned a fair bit about it because we've been getting up close and personal with it for a while now. But there's been a lot of data coming back, and some data that's been analysed has kind of given it a greener tick in terms of its potential for life. I mean, we've looked at it as a potential life-bearing part of our solar system for a while. But this has sort of added a bit more to the mix, quite literally.
Yes, it has. And it's all based, of course, on that most marvellous of all NASA ESA projects, the Cassini mission, which came to an end in 2017 when Cassini flew into the atmosphere of the planet about which it had told us so much, burned up in the atmosphere of Saturn. Actually, it didn't burn up because there's no oxygen in Saturn's atmosphere. It just melted because of the friction, the heat of the friction from the speed at which it was travelling through Saturn's atmosphere. So that's been the most marvellous source of data for scientists who are interested in the planet, its rings, and its moons. And of course, we learned directly from Cassini that Enceladus is one of those moons which has a rocky core, a liquid ocean overlying the rocky core, and on top of that, a crust of ice, which is probably in the region of 20 kilometres thick. The ocean's probably much deeper than that. And so that's the model that we have. And of course, that was largely proven by the fact that around Enceladus's south pole, there are ice geysers. There are these plumes of ice which squirt out from cracks in the ice surface. And so they're tiny shards of ice and water vapor as well that's mixed in with them. And as Cassini, as its mission took place, I think it was there for 14 years, 12 years, something like that. It was the early 2000s when it went into orbit. It's a fabulous mission.
Yeah.
And as the mission unfolded, the mission scientists were able to steer Cassini through these plumes of stuff coming out of Enceladus and actually analyze them, not just spectroscopically, but also by, the mass spectrometers and things that are on board. We're able to tell scientists pretty accurately what were in these plumes of water, vapor, and ice grains. And so we've got this itinerary of stuff, or inventory, that's the word I want, an inventory of stuff that is dissolved within the oceans beneath Enceladus's icy surface. And it turns out, and this is work, by the way, that's been done by a scientist called Dr. Christopher Glein and his colleagues at the Southwest Research Institute in Colorado, one of the leading planetary institutes in the world. What they have realized is that basically, in fact, I'll quote Dr. Glein, what we've learned is that the plume contains almost all the basic requirements of life as we know it. And then he goes on to say, and this is the new thing here, Andrew, while the bioessential element phosphorus has yet to be identified directly, our team discovered evidence for its availability in the ocean beneath the moon's icy crust. So what they've done is they've looked at the balance of what is in that ocean, and they've essentially said the thing that's missing here, but must be there because we know these other things are there, is phosphorus. So they haven't actually, they haven't detected it. So what Christopher goes on to say is the quest for extraterrestrial habitability in the solar system has shifted focus as we now look for the building blocks of life, including organic molecules, ammonia, sulfur-bearing compounds, as well as the chemical energy needed to support life. And he goes on to say, phosphorus presents an interesting case because previous work suggested that it might be scarce in the ocean of Enceladus, which would dim the prospects for life.
Yeah.
But now what they've done is these analyses. Essentially, they've done, and this is not Dr. Glein on his own. I think he's got a team of collaborators, colleagues who are researching with him. They performed thermodynamic and kinetic modeling to simulate the geochemistry of phosphorus based on insights from Cassini. And I'm quoting the phys.org article about this there because they tend to put it in a very succinct fashion. And this is about the ocean seafloor system on Enceladus. And so this geochemical model that they've evolved as to how the seafloor minerals are dissolved into the ocean, that actually predicts that those phosphate minerals would be there and would be soluble in the ocean. So, quoting again from Dr. Glein, the underlying geochemistry has an elegant simplicity that makes the presence of dissolved phosphorus inevitable, reaching levels close to or even higher than those in modern Earth seawater. What this means for astrobiology is that we can be more confident than before that the ocean of Enceladus is habitable. And he goes on to say, and this is, of course, what we all think, we need to get back to Enceladus to see if a habitable ocean is actually inhabited. And I think so say all of us.
That's one thing. And if the day comes where we can get back there and we can get down into the ocean and do some sampling and maybe find a Babel fish or two.
Yes. Yeah, that's right.
We'll be able to talk to them as well, which would be
We
good.
would then, yes, that's right. Yeah. Absolutely.
The next phase is testing whether or not that life is the same kind of life that we have here, or if it's a totally different development unto itself.
That's right.
That would be amazing.
If you've got DNA to sequence and things of that sort, who knows what you might learn. So it is interesting that certainly NASA and other organizations have got missions to Enceladus in their on their bucket list. They do want to send a spacecraft to Enceladus. And you might remember we spoke a few years ago now with and about Linda Spilker, who was the Cassini mission scientist. She came over from the States and did a lecture for us here in Australia. And she was certainly then, and I bet she still is, part of a project called EEL, which I think was something like Enceladus exobiology experiment or something like that. I can't remember. But the idea of EEL was that it would worm its way through cracks in the surface, an eel-like robot that would worm its way down through cracks in the surface of the ice, eventually pop out into the ocean beneath and tell us what's in there. Yes. I guess the only problem with that is you want to be very careful you don't take earthly microbes down with you that might kill everything that's already in the ocean. Yeah. So,
well, I think for the earthly microbes, it might be a hostile environment. They may not survive.
They might not survive, that's right.
Yeah.
On the other hand, they could just say, wow, look at this, all this phosphorus, this is fabulous.
Yeah, well, we've certainly proven that introducing foreign species into different parts of the planet sometimes works in their favour rather than ours.
Exactly. We've got some great examples here in Australia. Yes, cane toads.
Did you hear they've actually found some in Lake Macquarie?
I didn't know. That's not far from you. I didn't hear that. Gosh, that's getting south. Yeah.
They have a what do you call it? A quarantine line around. I think it's Coffs Harbour on the north coast of New South Wales. Their wells, they're 500 kilometres south of it. Now, they don't know how they got there, whether they were brought in on purpose or they were hitched a ride on a truck. But they found a little colony of them in Lake Macquarie.
Wow.
That's very scary.
It is. Yeah, it is.
But, they're not a fun creature. But they're not the only ones. We've got rabbits here as well and foxes and you name it.
Humans.
Yeah, human. Well, that's true.
Yeah, no, and I should clarify that because, I mean, Anglo-Saxon humans largely introduced species. Yeah.
If you go back 60-odd thousand years, 80-odd thousand years,
that's true.
This continent either.
No, that's right.
So, we migrated, we moved in.
Yeah.
You can argue it any way you like. But
that's
the
right.
fact of the matter is these things happen. And look, Enceladus is very interesting and certainly the focal point of potential life in terms of what it can offer. It's not the only candidate, though. I mean, you've got a couple of other ice moons out there. Europa
Indeed.
is one with potential, and Ceres, I believe, could be a candidate.
Could be, that's right, which is nearer than either of those two. I think Europa is the one that most missions are focused on, though. And in fact, Europa Clipper launches, is it next year, I think, which is going to orbit Europa, and hopefully will tell us much more about it.
Yeah, and I mean, I've even read that Ganymede and Callisto could be candidates.
Yeah.
So wouldn't it be great if there was life on all of them?
It would be incredible. And I hope we would be able to report it on Space Nuts, Andrew.
I hope so too. It's got to be out there, Fred. Some kind of life, even if it's microbial, it's got to be there. And we're still sort of waiting and hoping that we'll be able to get samples from Mars eventually through the Perseverance rover and analyse that to see if there was any life previously on Mars. I mean, we've already done the maths to prove that Mars existed with atmosphere and liquid water for long enough to create life.
Yeah,
I assume.
Right. Yep. No, I think that's true. Life seems to kick off very quickly in the right circumstances.
Well, it does. I mean, just look at the mold and mildew on my wall.
Yeah,
that's what we'll find. Mold, mildew, and babelfish. That
green slime. Yeah.
Yeah, that stuff grows everywhere.
Let's just hope the babelfish aren't too slimy, because you've got to stick them in your ear, if I remember rightly. Yeah.
Who on earth thought of that idea?
It might have been a guy called Douglas Adams, I think.
Yes. All right. We watch with interest the prospects of life on Enceladus or inside it, as the case may be, and hopefully we will find out in the not-too-distant future. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
Space Nuts.
Now, Fred, from one small object in our solar system to many, many, many thousands of large objects in the universe, and we're talking about galaxies. And astronomers have been mapping a whole bunch of them, 56,000 of them to be exact.
That's correct. Now, at first sight, this story looks like a, well, so what? Bearing in mind that I myself was project scientist for a project that allowed us to map 136,000 galaxies, and I was very closely attached to another one that mapped half a million galaxies.
Wow.
As well. The 6DF Galaxy Survey and the 2DF Galaxy Redshift Survey, respectively. These were.
This sounds like chump change then.
Yeah, that's right.
I'm pretty sure there's something more to it.
There is something more to it, because our surveys that were done with the Anglo-Australian Telescope and the UK Schmidt Telescope, the ones I was involved with, they use the standard method for determining the distances of galaxies, which is to measure their redshift. And we know from the time of Hubble back in 1929 that the higher what we now call the redshift, but it used to be called the recession velocity, the speed with which a galaxy is moving away from you, the higher that is, the further away the galaxy is, and there's a relationship that links the two. So that's the standard method. But of course, that depends on you knowing what the link between the velocity of a galaxy as measured by its redshift, in other words, the speed of recession, the link between that and its distance. You've got to know that. And so what you need is independent methods of measuring the distances of galaxies that don't necessitate the use of the redshift. In other words, you're not relying on what we've learned so far to measure the distance of the galaxy. You're not picking yourself up by your own bootlaces, in other words. And that's what has happened here. So these 56,000 galaxies, and I think this is quite a large team of scientists who've done this work, principally in the US, I think. That team has basically used methods that are independent of redshift to measure the distance of the galaxy. And there are some which you would know about and some that you might not. And some of them I'm probably a bit rusty on because I haven't thought about them for a long time. But you probably know that the way that we first measured the distance to galaxies, and this is what Hubble based his work on, was the use of variable stars, things that we called Cepheid variables, which were discovered by a female astronomer by the name of Henrietta Leavitt. She discovered that they have a relationship between the period of variation, so their brightnesses vary in a regular fashion, and the period of that brightness variation is directly linked to their intrinsic brightness. In other words, if you can measure the period of one of these things, you know how far away it is, independently of anything else. And so that's how the first galaxy distances were measured. But of course, to do that, you've got to be able to see these stars. And that means that as you look further and further into space, galaxies just tend to be so far away that all you're seeing is a blur of light rather than individual stars. But for galaxies out to quite reasonable distances, they have been measured. That's actually why the Hubble telescope was built, to measure Cepheid variables in other galaxies, more distant galaxies than we could see, with ground-based telescopes. So that all is fine, and that's one of the methods that you use to get an independent distance measurement. But there are others too. One of them that I remember from my days working in this field is something called the Tully-Fisher relationship. And just hope I'm remembering this correctly, but it's about the way galaxies rotate and their rotation speeds, which once again you can link to their intrinsic brightness, and because you can measure the brightness of a galaxy from the Earth, then you can calculate its distance. So what these scientists have done is they've used 8 different methods of determining distances, like the things that I've talked about. In fact, as the Cosmos website puts it, the measurements were made with 8 different methods, from looking at tiny color changes to brightness fluctuations and tiny tweaks in the motion properties of galaxies. So that's essentially the method. And what they've done is been able to use that to get an independent measure of the Hubble Constant, which is the number that defines how fast the universe is expanding today. And as you and I have spoken about recently, Andrew, that is a controversial figure because two very, very good and secure methods give you two different answers for what is supposed to be the same thing. So the method that has been used to make these measurements is it has given a value of the Hubble constant. I'll just quote the units because they don't mean that much when you hear them first. The units are kilometers per second per kiloparsec, and what that means is a kiloparsec is it's obviously 1,000 parsecs. A parsec is 3.26 light years. So for every I beg your pardon, it's not per kiloparsec, it's per megaparsec. Get it right.
Okay.
So long since I've thought about this. So it's 75 kilometers per second per megaparsec. 1 megaparsec is 3.26 million light years. Okay. So an object at that distance from us will be receding at 75 kilometers per second. At twice that distance, 6.5 million light years, it would be receding at 150 kilometers per second, and so on as you go further and further out into the universe. That's what the Hubble constant tells us. So it's a number with a gobbledygook set of units, kilometers per second per megaparsec, but that's the quantity that we're aiming for. And the current number is 75 that has come from these measurements that were made in this story with an accuracy of 3 kilometers per second. Yeah. So that is quite a narrow range of uncertainty, but the big but, and that is if you use the cosmic microwave background radiation, which you can also use to work out what the Hubble constant is by looking at the patterns of light and dark in it. Remember, that's the microwave signal that surrounds the whole sky. It's the flash of the Big Bang that we're seeing as it was 13.8 billion years ago. For that, you get an answer of 67.5 kilometers per second per megaparsec. With a 1 kilometer per second uncertainty. So these two very accurately known numbers don't agree. And that is one of the current big conundrums in cosmology. It's what you and I spoke about some weeks ago. Yeah. And it doesn't look as though this problem or this quest to measure all these galaxies has helped, because it's given you a 75 kilometer per second answer where you expected 67.5 kilometers per second.
It doesn't sound like much, but over the cosmic distances we're talking about, it's massive.
It is massive. That's right. Absolutely. And, they come with such small errors. I've told this story before, Andrew, but when I was starting getting involved with all this stuff in the 1970s, there were two camps of scientists, both believing they had the right answer, one of which said the Hubble constant was 50 kilometers per second, and the other said it's 100 kilometers per second. And when the Hubble telescope itself was used to actually investigate this problem, lo and behold, the answer came out at 75 kilometers per second, which is actually confirmed by this new value from the 56,000 galaxies that have just been measured. So it hasn't really helped all that much.
You can't write off the 67.5.
You can't. That's right. You can't. So the story continues, and I think this is one that we will cover again at length in Space Nuts.
So I'm just looking at the article you've been discussing. Where does the standard candle fit into all of this?
So, yes, that's just a way of saying if you know how bright something is, and if you know how bright something is intrinsically, in other words, what its brightness will be at a standard distance. Say a street light. If you know how bright it is when you see it from 10 meters or something like that, then when you see a street light that is the same at distance, if you can measure its brightness, what you can then do is work out its distance, because it's got a certain brightness at 10 meters. And that's fixed, that brightness doesn't change, but what does change is the distance. And so if you can measure its brightness when it's at distance, it's a fairly simple calculation to get from that to the distance between you and the unknown lamp. That's the standard candle idea, and
that's based on supernova.
Yes, that's right. So that's actually how Brian Schmidt and Saul Perlmutter did their work that determined that the universe is expanding ever more rapidly. The fact that they could measure supernovae, which they assumed were standard candles, and we still do, because we know their intrinsic brightness. That's what demonstrated it. So standard candles are very accurate, but they don't agree with the cosmic microwave background radiation.
Yeah. Oh, very. Yeah. I'll be really thrilled to see if someone can solve this one day. They'll probably win a Nobel Prize or something, because it's
they might well.
One of the great mysteries.
Strangely enough, I've got a half-written email to Brian Schmidt about a completely different answer sitting on my computer at the moment. And when I finish it off, I might say, "What do you think about all this?" I'd be really interested to know.
You have an idea?
I don't think I've got an idea, but he's one of the world's leading cosmologists. He might say what he thinks about it. Yeah. I don't think I will, though, because he's a busy man. He runs a university and he doesn't have time for trivia like the expansion of the universe.
Yes, about that.
Yeah. And Brian, if you listen to Space Nuts, I do apologise for all this.
I'm sure he'll understand.
He's a great friend.
Listen to Space Nuts. I'm sure he's got time to read an email from the great.
Yes, he might have. Yeah, he's a great friend of astronomy, is Brian, and a great supporter, which is excellent.
Yes. So what we're basically saying in regard to this mapping of near 56,000 galaxies is we still have a differential we can't explain.
Yes, that's the bottom line.
Okay.
I couldn't have put it better myself, Andrew.
You probably could. But thanks anyway. All right, we're going to leave that there, but I'm sure we'll come back to it at some stage.
I think we will too.
We unravel the mysteries of the universe here on Space Nuts.
3, 2, 1.
Space Nuts.
Now to our favourite part of the program, which is the end. No, it's not. It's our question time. Although this is not a question. This is a statement from one of our regulars, Rusty in Donnybrook, who usually sends us audio questions. But he felt compelled to write this one down. Now, I'm going to read some of it. Not all of it, Fred, but I think we can get to the gist of it. He's talking about Pluto and Charon. I think that's how it's pronounced, or Charon, Charon. We'll call her Sharon. Mate.
Sharon.
Pluto, he says, the Pluto-Charon barycenter is 938 kilometres above Pluto's surface, or about 1/13 of the distance to Charon. If I ask how many moons does Pluto have, any answer but 0 would be wrong. All the bodies in the Pluto-Charon system revolve around a common point which is outside of all the system's members, calling Hydra and Nix satellites or moons of Pluto the dwarf planet is completely incorrect. They orbit the binary system. Only Pluto and Charon have reached the IAU's standard for planet or dwarf planet in that they have achieved hydrostatic equilibrium or roughly spherical shape. So what he's suggesting is the Pluto-Charon system is a binary planet and should be known as such, and that we can get rid of the term dwarf planet forever by defining Pluto and Charon as a singular rank binary planet in our solar system, and it would be rare, probably the only part of our galaxy that might have something like this, or certainly the only thing in our solar system. So, with Pluto losing its planetary status in, I think it was 2006, if I remember rightly, there's been a lot of debate about whether or not that should have happened. I think you were on the pro side of the argument, Fred, so it's now officially a dwarf planet, because of all the other things out there that are dwarf planet-ish. But now Rusty is suggesting, well, maybe we've got it wrong. Maybe we should be looking at them collectively, and Pluto and Charon, a binary planet, one entity orbiting a fixed point. What do you think?
Okay.
Thanks, Rusty, for the idea.
Yeah,
it's a great debate question.
In fact, Rusty's full email reads like a kind of manifesto. This is where we stand. And it's great to have that. And everything that Rusty says is correct. That Pluto and Charon, as it's normally pronounced.
Sharon.
We had a discussion before the show, didn't we, about how you should pronounce this? And I said, don't call it Sharon. Sharon. Anyway, yeah, I've heard NASA people call it Sharon, so that's all right too. You can call it whatever you like. I call it Karen.
Fair enough.
Yeah. So it's true. They are a binary object and orbit their common barycenter, center of gravity. It doesn't change the definition of them as a dwarf planet. Ooh. Or the definition of Pluto, because a dwarf planet is one that has not cleared its neighborhood in space, either by gravitationally binding objects or by scattering them out. It hasn't cleared the debris from its region of space because Pluto is just part of a large cloud of objects, icy asteroids, that we call Kuiper Belt objects. And so it's still a dwarf planet. I think there's a good argument, though, for Pluto and Charon being described as a binary dwarf planet.
Oh.
Now, I think that's fair enough because, in a sense, they are. Because, as Rusty points out, Charon also satisfies the definition of a dwarf planet because it is in hydrostatic equilibrium. It's a spherical object. It's comparable in size, about half the diameter of Pluto itself. So it's a large object, and that does make it very much a binary pair. So I think there's a good argument for describing them as a binary dwarf planets. But such objects may not be uncommon. That's partly because we know that in the world of asteroids, whether they're icy out beyond the orbit of Neptune or whether they're in the main asteroid belt or indeed nearer to the Earth, binary asteroids are common. We've been talking about one all week, the binary asteroid Didymos, which has a moon. It's not actually a binary because the center of mass is still within Didymos's bulk, but it's still a dual object. It's still an object with a satellite. So things like that are quite common, and there are certainly other objects which we know have the barycenter outside the main object. So they're not that uncommon. It's certainly not the case that you would use this argument to promote Pluto to planethood. I also think that to describe the other four moons of Pluto, other than Charon, as non-moons because they don't orbit a planet, I think that's stretching. I think the definition is technically correct, but I think you might expect to define a moon as being an object that is subsidiary to the main object in the system, if I can put it that way. And in that regard, Charon's still a moon of Pluto, as are the other four. And so I think that's there's a little bit of, playing around with words here. And I think you could argue either way. My argument is that it just gets far too complicated and sounds far too pedantic and far too, the word I was going to use is anal, which is perhaps not the right word, but you know what I mean when you really focus on the tiny minutiae. I'm not sure that you can. I'm not saying that. I'm not accusing Rusty of anything like that. Of course, he's a good friend, and these debates are great. But it's not.
That's Rusty.
Just sending. It's my other half who's tried to call me 3 times today, and I've either been in a meeting or a colloquium or a podcast recording, so it's one or the other. So I think it's. I think it's far more understandable if you say that these are moons of Pluto, even though technically Rusty is absolutely right. They're not. They're moons around a pair of binary objects.
Yeah, if we did do this, he's suggesting that the formal designation for Pluto should be Pluto A, being Pluto, and Pluto B, being Charon.
Yeah.
He does the comparison with Alpha Centauri A and that system, even though they're stars. But
yeah, and in that regard, I think there's an argument for that, because when Charon was discovered, it would not have been known that its mass was high enough to pull the barycenter out from Pluto's bulk. So which we know now. But the naming of objects is, as you know, it's an absolute minefield, as we're realizing now with so many of the things that we talk about. So Pluto A and Pluto B, I quite like the sound of that.
Yes. You might be onto something there, Rusty, but thanks for bringing up the argument. It's a great debate topic and one that geeks around water coolers of the world will probably ponder for who knows how long.
That's the word I was using.
Thanks, Rusty. Lovely to hear from you. Let's go to an audio question. This one comes from Wim in Toronto, who we don't usually do cooking on Space Nuts, but we're going to do it today. Take it away, Wim.
Hey, Andrew and Fred. This is Wim Lowtender, Toronto, Canada. I have a question about light and how we harness it to cook. If microwaves use microwave radiation to warm up food and drinks, why don't we use infrared or even UV light? From what I understand, IR and UV are more energetic wavelengths. Wouldn't these heat up items much faster, possibly even instantaneously? Your podcast has me leaving work with more knowledge and insight about the universe every time. Keep up the amazing work. Thank you so much.
Thank you, Wim. That's lovely of you to say. And an interesting argument again, I suppose. We cook with light. We use microwaves. Just about every household in the Western world's got a microwave oven, and everyone ignores the beeps and opens the door before they finish, but that's your problem.
I don't anymore after you told me what they were for, because I hadn't realised that.
I'm told, in case people don't know, the beeps happen 4 or 5 beeps after the cooking's finished so that the microwaves scatter and then it's safe to open the door.
Absolutely.
I understand it. It's not there to remind you time and time again that you're finished cooking your food. But UV or infrared, would they be better than microwaves?
Well, it's a very easy experiment to do because all you need is a radiant heater and something fresh out of the freezer, and you try heating it up with your radiant heater. Whether it's basically something that gives you warmth through infrared radiation. That's what that's all about. Yeah. And what happens? Well, the surface that is being irradiated melts and probably would eventually go black if you had enough heat, and the rest of it stays frozen. Yeah. So it's just the different way in which these various radiations interact with matter. So ultraviolet probably would make bits of whatever you're trying to cook fluoresce, because that's high energy stuff, and light itself, which is what the UV would generate, is also energy. But neither of them are appropriate to try and jiggle the molecules inside a piece of meat or a piece of bread or whatever it is, or a liquid, to warm it up, because that's the beautiful thing about microwaves. They will penetrate into the interior of an object, and they will stir up their molecules. They'll make them vibrate, and we call that vibration heat. So it warms it up all the way through, rather than just irradiating one surface and turning it black, as it would with a piece of toast if you held it too near a heat source for too long. So it's
a toaster, isn't it?
I'm sorry, say again.
That's what happens in a toaster.
Exactly. Yes, that is what happens, and that's how a toaster works, by infrared radiation falling on the toaster. So if you want things toasted, that's the perfect way to do it. But if you want them cooked, with their interior also getting cooked, microwaves are the way it works.
And you know what? This is why the vertical grill was such a disaster.
Yeah, that's right. Yeah.
Does anyone still use one? I remember when they were big in the 70s, my mother got one, and I think she used it once and went, I don't want to use this thing ever again. Horrible, horrible things.
I'm not sure we had those in the UK. Maybe they were a peculiarly Australian invention.
Yeah, probably vertical grill, but they used UV. They were just basically a sideways grill system rather than sticking it on a tray under the top shelf of the oven. Same concept, just
was it UV or infrared that they used?
It was a, what do you call it?
It was a heater.
It was, but I wouldn't know. In my childhood, I was too dumb.
No, you weren't. Not at all. UV, though, just thinking about that, it does. UV can sterilize surfaces, so it does kill microbes without necessarily cooking what the microbes are living on. So you can sterilize things with UV.
Yeah, a lot of public facilities, let's call them, use those hand dryers with UV light to when you're drying your hands after you've been to the public toilet, you get a UV light blast to kill the microbes.
That's right.
Yes. No, I'm not sure about the vertical grill. I think it just had a basic element in it, to be honest.
Yeah, so it's probably infrared that it tried to use. Yeah, that's an interesting idea. I've not come across that one before.
Yeah, it's a good idea, but not overly practical in the kitchen. But, appreciate your thoughts, and thanks for sending in your audio question. And a reminder that you can send questions into us as well, or you can make an observation like Rusty did and put your case forward, and Fred will shoot you down in ultraviolet flames.
I hope I didn't do that, because I think it's a good idea, and it's one that it's always great to have these discussions as well.
Yes, indeed. But yes, you can send us questions via our website, spacenutspodcast.com or spacenuts.io. And you click on the AMA tab and you can send us text questions or audio questions there, or on the right-hand side, there's a little tab where you can send us your audio question, as long as you've got a device with a microphone, which most smart devices have these days, and many, many computers now. It's as simple as that. Click the button, say who you are, where you're from, and send us your question. We'd love to hear from you. And you can also browse our website while you're there and check out the shop and everything else, and catch up with the back catalogue of Space Nuts. But you can also catch up with our new podcast, Astronomy Daily, which is a short-form podcast with me and Hallie chatting about the daily news in the astronomy world. So have a look at that as well. And don't forget to leave us your reviews. We love reviews, except the ones that we don't love. We don't get many, which is good. But leave your reviews through your favourite podcasting platform, because they help to spread the word. And while I'm talking about spreading the word, visit the Space Nuts podcast group on Facebook and chat to other listeners. A lot of people get together on there and share their photos and their ideas and their arguments. And, it's a great little community, that one. I pop in occasionally and just see what's going on. That brings us to the end, Professor Fred Watson. Thank you so much.
Oh, pleasure. Always good to chat. Thanks, Andrew.
Thanks, Fred. Professor Fred Watson, astronomer at large, part of the team here at Space Nuts, and Hugh in the studio, who did something today. Which is a nice change. That's it from us. Thanks for your company. And from me, Andrew Dunkley. Catch you next time on another edition of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.